So we are going to have our first keynote talk, and we have a great pleasure to have Professor Cristina Savin to give us a talk on computational building blocks for complex cognitions. Dr. Cristina Savin is an associate professor in neuroscience and data science at NYU, and her group basically studies the use of tools of machine learning to basically investigate the principles of adaptive computation in brain and artificial agents, by combining theory and statistical analysis of experimental data from many collaborators. So without further ado, let's pass to Professor Savin to give us a talk.
Michael. 1 second. Michael. Okay. Almost there. Thank you, everyone. Thank you for the invitation. It's not exactly my usual crowd, but I was telling people earlier that I think it's good to sometimes go out of your comfort zone and try to talk to people who are interested in similar things, but maybe not approach it from different kind of methodological angles. So I'm a computational neuroscientist, and what we try to do in my group is understand principles of complex adaptive behavior, primarily in brains, so the biological substrates of learning, but also trying to extract enough sort of like essence from the brain to be able to translate that into more flexible and adaptive artificial intelligence systems. And from that perspective, one key feature of brain cognition is how it comes about, which is gradually and compositionally. Okay, so to get us started, let's think about a concrete example. So assume that somebody came to you and asked you to start like juggling a bunch of balls while riding a unicycle. Now, I'm assuming that we don't have like people with like extensive circus experience in the audience, so you probably don't know how to do this from the start. So how would you go about it? You wouldn't like try to do this from the get-go, right? You try to break it into pieces and use what you know already. So assuming that you know how to ride a bicycle, you would translate that knowledge about how to ride a bicycle and attempt to learn how to ride a unicycle. If you're trying to juggle multiple balls, you're not going to start by juggling multiple balls, but like try to do 1, 2, 3, and sort of like gradually increase complexity until you reach like competence of some sort. And only when you know how to do these things individually would you try to put them together to achieve the final goal. Like this is like super intuitive for us. It's sort of like how our education system works. It is also how we train animals to do complex tasks in like neuroscience experiments. Like we don't like just drop them in the task and hope for the best. That would not work very well. But it's like fundamentally different from how we approach training in like artificial intelligence systems, where like the primary paradigm is arguably throw a lot of data at the target problem and hope for the best. Okay, which works most of the time. Like I'm not saying it's a bad idea, but maybe there's something to be learned from the way brains learned that can make the process a little bit faster and a little bit better. Okay, so what I'm going to talk about today is recently published work done by postdoc David Hawker, there on the top, in collaboration with the neuroscience experimentalist lab, Cristina at NYU. And I'm going to like sweep under the carpet over a bunch of details. So like if I'm not saying something, like I point you to this as sort of like the technical detailed reference. But hopefully we're going to have fun along the way. So the first thing that we're going to do is we're not going to start with the sort of like traditional curriculum learning type of benchmark. We're rather going to look at a task that's motivated by experiment. And it goes something like this. So you have a little rat that needs to decide how long to wait for a reward. So at the beginning of a trial, can you guys see my pointer in any form? It's like a very tiny dot. Okay, I'll just something different here. So here it starts a trial by poking in a central port. Then it hears a tone, beep, and the frequency of that tone tells you what the offer is for that particular trial. So different frequency correspond to 5 different possible volumes of reward. Now, a light communicates where the reward is going to come, but not when exactly it's going to come. So the wait time required until you actually get the reward is drawn from an exponential distribution, which corresponds to a flat hazard rate. Animal has 2 choices. It can choose to like wait until the reward comes, or at any moment in the trial, it can decide, okay, this is taking way too long, and it's going to go to the other port, abandon this trial, and restart the whole process. Okay, so on top of this, there's a secret catch. The experimental is sly. And there is a small fraction of the trials in which the reward never actually arrives. So the animals are forced to engage into the, yeah, I don't want to do this anymore option. And this gives us like an analog in time behavioral readout of how much value do the animals attribute to these offers as a function of the context. Okay, so simple enough. Now, maybe you're sort of like, it's hard to like get into the mentality of a rat. I'm going to try to sort of explain the same task from the perspective of a human. So before you came to the conference, maybe you wanted to grab a little bit of breakfast, and you had like your favorite place where you wanted to go, and you get there and you find a really long queue. And there's a question, do I like join the queue and wait, or do I try to find some other place to have breakfast? And this decision will depend on 2 different kind of dimensions. So first of all is the how much do I really want their breakfast burrito kind of thing. So like the actual offer of this particular option. But the other thing that determines your decision is the context. If I'm in a neighborhood with like a lot of good food options, I can just go around the corner, find a place with less of a queue, get food there, happy. If on the other side, I'm in a less option-rich part of the city, and I'm not going to tell you where these 2 little maps are from. There's a secret New York joke there. Then maybe I'm sort of like more willing to stick it out and like join the queue. Okay. So in the experiment, the way we do this is by manipulating the availability of different kind of rewards. So we have blocks in which all mixed box where all of the 5 options are available. We have low and high blocks where only like the best and the worst 3 of the options are available. And there's about sort of like 50 successful trials of making the transitions between these things. Like the important thing is that the animal doesn't really know when the world has changed. So it can only know from trial by trial, from actually experiencing the world, getting rewards, and seeing what kind of rewards it's getting, that the world has changed. So there's this like non-stationarity in the environment that the animal has to figure out and sort of like navigate around. Cool. So you can ask, okay, how hard is this? Like, what does it even like mean to do well in this task? So it turns out that like actually solving this task is non-trivial. Like you can't do it analytically, but we can write down a sort of an approximate MDP version of the task where we kind of cheat. Like we tell this agent absolutely everything that they need to know about how the world works, including when the block transitions happen, and ask, okay, this sort of like godlike agent, what kind of behavior would it have? And it has a couple of like very striking features. So first of all, it has this like linear dependence with the offered reward. So you should wait longer if there's a gooder reward waiting for you at the end of the road. intuitive enough. The other thing, so we're going to call this linear reward sensitivity. The other thing is that like the value of a particular offer changes depending on the context. So the same 20 milliliters reward is worth twice as much time. So I'm going to wait substantially longer if that's the best of a set of crappy options compared to when it's the worst of a set of good options. So we refer to this as context dependent. So this is what a godlike agent would do. This is what a rat does, which is actually not that different. So of course, like it's not perfectly linear, and exactly how long it waits is a little bit different. But the core features of the optimal behavior are already there at the level of single animals. And because Christine has a huge rat farm where you can automatically train hundreds of rats on this task, we have, like, this is an old slide, we have 300 plus animals these days. But basically, you can look at sort of like huge populations of rats and ask how systematic is this behavior? And we find that except for a few dum-dums that like never quite learned the task, most of the animals like behave appropriately. So they wait substantially longer for 20 milliliters when it's the best of bad options relative to the other way around. Okay, so interesting. Like how do they do it? So if we're looking at like very informative moments in this experience, it's like when the transition has just happened, like how fast do they change their behavior? And this is sort of like a transition between either mixed and low-high block or the other way around. And you can see that like relatively quickly, they adapt to the new environment, like signatures that have figured out that something has changed and they're doing something differently about it. The other thing that's kind of interesting to note is a little bit of a symmetry. So they're switching faster when they're going from low and high to mixed than the other way around. And there's a good reason for that in the task design, that is kind of like fundamentally asymmetric. So when I'm in a low or a high block, the moment I see a reward that's completely inconsistent with that scenario, so the moment I see one of the other two options that were not compatible with the original block, I get like a huge influx of information telling me, oh, the world has changed, I need to change my strategy. The other way around, all of the rewards are available, so they're possible under the original world model. So I only need to like keep track slowly of their like frequency of appearance and their statistics in order to figure out that the word has changed. Okay, so I don't have time to tell you about this in detail, but there's substantial work in Christine's lab that tried to model just the behavior of the rats and showing that it can be well understood as a form of Bayesian online inference, where basically what the animal does is keeps track of beliefs about what kind of world is it in, and then uses that in order to like dynamically modulate how long they wait as a function of different rewards. Now, it's still a very simple task. What's hard about it, like from a reinforcement learning perspective, is that there's sort of like a fundamental multi-scale nature of this task, that within a single trial, I need to remember what kind of offer I got. I need to wait substantial amount of times, and I need to like moment by moment decide if I'm staying or I'm going without additional feedback. So that's one time scale, and a very different time scale from trial to trial. I'm getting one bit of information, what kind of world am I in, and I need to sort of like update my beliefs about the state of the world from that. So very long temporal horizons, sparse feedback. So this makes it hard, although it's kind of like, yeah, you're able to grab a reasonable breakfast this morning. You know how to do this. It's not that hard. Okay, so we wanted to ask, how do we make an artificial agent that does this? And yeah, it turns out to be hard. So what we did is sort of like we set up a DeepRL framework where we train agents with exactly the same kind of task that the animals get. And if you just like do it from scratch, machine learning tools thrown at the problem, you very quickly run into like annoying business. So first of all, you get a lot of agents that just cheat in a stupid way. So like, you can't have infinitely long waiting horizons during training. That would just like break your machine. So like we have to like enforce a maximal trial duration just to get the deep RL agent to get going. And then sort of like, oh yes, if I do nothing, I kind of get some reward. It's a suboptimal solution, but it's like compatible with some people's worldview. So yeah, so the agent does nothing. It doesn't care. And sort of like it just opts out once in a while. Like the other thing that's sort of like, it's another sort of like salient suboptimal solution where it just goes with the average reward. So I will work harder if there's more reward to be had, which is kind of the opposite for the optimal strategy. So the red and the blue lines are flipped relative to the purple. Okay, so of course, we spent a lot of time like throwing all sorts of machine learning tricks at this problem, but we couldn't quite get it to work. And in order to like move forward, we had to go back to the brain and sort of like think about, okay, why do these rats can do it, and why don't our agents learn it? And of course, sort of like the answer here is the gradual skill acquisition. When we throw the rats into this experiment, they already know stuff. Like they know how to keep information in memory. They know how to keep track of time. They know stuff. So we decided that sort of like the solution forward would be sort of like to take our RNNs to kindergarten and get them to actually have some skills before they start trying to do this experiment. Sort of like a big cartoon description of how we go about it is that we try to sort of like pre-train the reinforcement agents with a collection of primitive subtasks, so like skills that you need in order to get going. And then we use behavioral shaping in order to link this together to actually work your way towards a task that you actually want to solve. Okay. And you can ask, okay, so like, how do I build the right primitives? So remember that we had this like MDP approximation of what the optimal behavior in the task should be. I didn't show you the math before, but sort of like the optimal policy looks something like this. So this is the Q value as of different states, and you can look at sort of like a few key ingredients in the solution. So first of all, you need to know what the offer on this particular trial is, so what the reward at trial N is. Then you need to keep track of how often, like how long, how much time has elapsed during the trial. And then you need to know something about the average reward in your particular block condition. So like the general opportunity cost for that situation. So we decided that these are sort of like useful subcomponent tasks and that we can train separately with supervised learning objectives. So we have like a little memory task where we train the RNNs to keep inputs in memory for a while. We have a counting task, which is like increments over time, so that it's a passage of time kind of task. And we have a bunch of tasks that have to do with like figuring out what kind of block you're in and keeping track of average rewards that you've been getting in past history. So sort of like there's an integration of inputs that's sort of like the average reward, running average kind of thing. And we have like an inference task that tries to infer different possible latent causes from a set of observations. Okay. So again, like each of these are sort of like our correspondence of the original map problem. Once you've pre-trained with this, then we go into behavioral shaping, which is exactly the same behavioral shaping that the rats go. So they start doing just the mixed blocks without lying. Then we introduce the lying. So like some fraction of the trials, there's no reward even if promised. And then at the very end, we end up at the task that we want, which is introducing the block structure. Okay, but this is, again, literally copying what the experimentalists do with their rats. Okay, so didn't tell you exactly what this artificial rat is, but it's basically, the architecture is kind of motivated by a combination of biology of computational goals. And we couldn't play with it too much, but there's an inference module that we pre-trained to do inference kind of things in the context of the kindergarten. And there's a policy module which gives you values and policies. The offer information, so the beep that tells you what kind of reward you're going to get, goes to both of these. And motivated by the meta-RL architecture of Jane Wang, we add additional information about the action and reward to the inference model. Like sort of like the idea is that you should be able to adapt to changes in context through the dynamics of these networks as opposed to changing more parameters so that it's fixed at the end of the full training process. Okay, of course, we need to train all of these additional supervised objectives. So we have like separate headers for those tasks individually, and they can go to either of the two modules depending on the task. So you end up with a total loss of this form where you have the reinforcement learning traditional stuff at the beginning, plus we regularize by all of the kindergarten tasks as auxiliary objectives. So we're making sure that we know how to do these things as we're training. Okay. So this is kind of the end-to-end training process. And finally, we get some agents that are not idiots. It took us half a year. It was hard. Okay, and sort of like, because in the rat, we have these behavioral models like fit to the outputs of the animal that sort of like infer from moment to moment what kind of things the rat believed about the world as they're going. Like we have a pretty like similar, like a strong similarity between what these agents end up doing and what the rat ends up doing in general. Okay. So what did we gain from this? So it turns out that with this kindergarten training, you speed up the learning process orders of magnitude. So like we kept having our reviewers asking, like, what if you double the training time? What if you double the training time? So we kept doubling the training time, and I can tell you it doesn't help. So if you just train from scratch in the final task, you do terribly. If you just add the shaping part, it helps a little, but not enough. And you need the full kindergarten experience to really get the bang for buck, to actually get the tasks to behave properly. So this is in like a learning rates kind of sense. You can ask, okay, do you need all of them? You can think sort of like the inference about the state of the world is the hardest of the kindergarten tasks. You can ask what happens if you just do that. And sort of like there is a decrease in performance. It's kind of interesting, and it's like a thanks to a nameless reviewer, is that the working memory only task, where you just train keeping information in memory for very, very long times without anything else, ends up doing quite well. And it doesn't improve over the other stuff, but sort of in terms of like baseline reward rates, it does equally well. What's interesting is that even between these two agents that were kind of doing similarly in terms of average reward rates, there's still differences with respect to how they solve the task. So the offer sensitivity and the wait time ratio, or the context sensitivity, are like formal markers of like how Bayesian-like the agent is. And the rat is in the black corners together with the kindergarten, but the working memory only pre-training procedure, although it gives you good offer sensitivity, it gives you like substantially poorer context sensitivity. So like there's an indication that different curricula might lead to different computational strategies for solving the task. The other guys are idiots. So like just one of the other tasks on its own, they're like not only terrible in rewards, but they're also sort of like fundamentally very different compared to how the animal solves the task. Okay, so the kind of like a couple of interesting things for us from this is like, ooh, if there are multiple ways of doing well, there might be sort of like the different rats are doing different things. So this like set out an entire separate project, like trying to understand the cross-animal variability in behavior and how that could be like traced down to different computational strategies. And yes, it's sort of like there's something still to be explained about what does the kindergarten curriculum do in order to sort of like bias the solutions towards better outcomes in a sense. Okay, cool. So again, like from a purely machine learning perspective, you can ask, okay, that sounds like a lot of hassle. Like, did you actually need to do all of those things? And the answer is, like, the curriculum does matter quite a bit. So we try to do sort of like tasks with comparable level of difficulty that were sort of like not matched to what the target task needed to be. And you see like substantial like decreases in performance. So it's not like any difficult task that you're training is going to help. We also tried to not do the pre-training, just do regularization as an auxiliary objective while training the final task. That also came with costs in performance. So we also sort of like try to see like, can I sort of like change the level of mismatch between the exact form of the pre-training tasks and the one that you need for the final task, but changing sort of like the structure of the inference problem. So like make inference with a lot more states and stuff like that. And you still maintain benefits. So maybe it doesn't have to be like perfectly aligned. If you're sufficiently aligned, you already get benefits. Yes. There are like 25 pages of supplementaries about all of the other things that we tried that I will not have time to go into. Start easy was the only like punchline that was kind of important. It's like, if you care about the order in which you're doing things, start with the simple task and add complexity as you go. That seemed to matter. Okay, so for now is talking about this kindergarten curriculum learning procedure where you take simple tasks that are kind of useful for the target and train them separately with a supervised objective before going into the actual job. And again, the right kind of pre-training is really defined by the compositional structure of the target task. Having an auxiliary objective helps a little. So like dropping it all together does decrease performance. So there is a reason to keep that on. And like the MDP really like saved the day, because sort of like you could have like maybe imagined what kind of tasks are useful. But having like a formal description of computationally what you have to do in order to solve the final task, even if approximately, really steers you in the right direction. And I forgot to say something that's kind of important, is like if you think about hierarchical reinforcement learning or traditional curricular learning, usually the subcomponents of the tasks are a sequence of operations that you need to do in order to solve the task. So there's most of the compositionality that we're thinking about traditionally is in form of sequences. Like this is not the case here. Here we're talking about multiple computations that you need to like perform in parallel and then bring them together in order to drive the behavior. So that makes it a little bit different, and maybe sort of like less intuitive to identify what the pieces are in absence of some sort of approximate like solved model. Okay, so we got the places, but how? Like, how can we understand something about the mechanics of this whole thing? So because we're sort of like collaborating with experimentalists, we were sort of like trying to develop some statistical tools to do data analysis to reverse engineer what's going on under the hood. And the fundamental unique feature of our task is this sort of like having like two very different time constants at which computation needs to happen, the within trial and across trial dimension. So we baked that into a hierarchical latent dynamical system model that now you can fit to either actual recordings from brains of rats or to the representations in these modules of our artificial agents. Okay. And basically sort of like what this allows us to do is sort of like try to separate within trial computation from across trial computation. Like in the artificial agent, what this gives us slow latents that have the same kind of structure as the behavior. So you have like different latents depending on what kind of block you're in and what kind of reward you're getting. You also sort of like start seeing this sort of like fast transitions in beliefs in the same kind of latents. And at the fast time scale, you see the encoding of reward and the passage of time. The same kind of things, maybe not exactly in the details, we can find in the neural activity in brains of rats doing this task. So there's sort of like a neural parallel that how these two agents are doing the tasks is somewhat similar. And this is particularly interesting that this sort of like incongruent trials. So the first trial, when you know for sure that the world has changed, because the slow latents like have like really abrupt dips that sort of like reflect the changes in the beliefs. And that's true both in the data and in the artificial agents. Okay, so we know that we have like super long time constants involved. That kind of indicates a little bit of like what mechanics should we be looking for in these agents. So first of all, you can ask, okay, what did the learning process do in very like brute force terms? Like how much did the parameters of the RNN change as I'm going through my super sophisticated, super multi-stage training procedure? And what you find is, yes, you converge quickly early in training. And stuff like the inference machine. So when you're introducing the inference task, then you see a pretty substantial reorganization of the parameters. And there's like smaller but still substantial reorganization as you're going through the later stages of the process. So inference does something substantial, just by brute force, like magnitude of effects. But we can look in more detail at the dynamical system structure that are being learned, because you need slow features like attractors or approximate attractors in order to keep information around for very long time constants. So looking for slow modes of the dynamics from a dynamical systems perspective is supposed to isolate how did the agent do it. And if you're just like, we have a numerical procedure for just extracting all of the slow points of the activity at different stages of the training process, you find something like this, that you start with a couple of attractors. During inference, when there's big reorganization, what happens is you're making a lot of dynamical systems features. And then you're trimming them down in order to sort of like converge to potentially a good solution. Okay, so this is kind of like just the numbers. You don't know that all of these things are visited actually during the task or that they're functional. But we can actually like zoom in at the end of the learning process to figure out what the agent learned. And this is like, if you haven't seen one of these things before, this is a kinetic energy landscape. So the color tells you how fast you're moving away from that state. And those are some little trajectories of trials from individual kind of blocks. This is the flow field, so like which way you're going as a function of where you started from, according to the sort of like the spontaneous dynamics of this thing. And what we find is like, if you haven't seen these sort of things before, like you have to squint, like this is like expert knowledge, but basically you find a few slow points that are kind of like spanning the space where the activity actually lives. And if you sort of like look through the perspective of the readout that decides beliefs about what kind of block you're in, different regions of the state space correspond to different kind of beliefs. So I have one slow point in each of these regions, so that this allows me to keep information for, I believe that I'm in a slow block, I believe I'm in a mixed block, etc. Okay, so this is a slightly different architecture. The first one was an LSTM. This is a GRU. GRUs look prettier, so I'm going to show you the rest of the plots in GRU space. But basically, it's the same kind of plot at a different network. And here I'm showing you in different colors, blue being not very visible. If I am in a block of different kinds, and I'm getting a 20 milliliters offers in this particular trial, what happens with the dynamics? Basically, like these lines are kind of parallel, and they're parallel to the horizontal line that corresponds to beliefs about being in different blocks. That means that I'm not really changing my mind all that much, which is kind of like the optimal thing to do. A 20 milliliters thing is the thing that happens in all sorts of blocks. It tells me absolutely nothing about the state of the world. Similarly, if I'm now in a mixed block and I give you different kind of offers, that will shift you left and right. Like so the dots are the starting points, the wiggly lines are the end points. You don't always like last equally long, so those are more noisy. But basically, it moves you along the belief line. So if you're seeing a bad reward, you're more likely to think that you're like going towards a bad world. If you're seeing a really good reward, you're more likely to think that that's sort of like the high block is coming. And what's super important is remember that we had this other agent that had a different training curriculum. that had similar reward rates but different behavior from in the details. Like those guys have fundamentally different flow field landscapes. So they do the same computation, but in a fundamentally different way that we still don't completely understand. This stuff relies on transients. It's kind of weird. And like if you're looking at the policy network, then this is kind of like also relying on slow features, but on transients around it. So different reward offers put you at different initial conditions, and that take you on paths that are either short or circuitous towards the region where you're deciding to opt out. So that means that if I'm getting a good reward, I'm more likely to stay. If I'm getting a crappy reward, I'm more likely to opt out quickly. In different blocks, the same picture emerges, but the location of where the attractor is changes relative to the decision boundary by virtue of sort of like getting this input from the inference network. So that means that I'm going to do the same kind of thing, but exactly how long it takes me to the point where I decide to opt out will shift. So that means that I'm going to wait longer for low block relative to the other stuff. So all of the things that we are seeing at the level of the behavior can be understood in terms of these dynamical systems features that the network built in order to solve the task. Okay, cool. Just to drive this point home a little bit more, if you're comparing the kindergarten learning procedure with all of the other training procedures, including ones that had good reward rates, it's unique to the kindergarten training procedure that you have all this extra dynamical systems structure. So basically, the take home from the lens of what did you do to this network in order to make it do better is that you build a lot of slow features into it. And then when you're going into the target task, you can just like tap into those skill set in order to sort of like do complex computations. I don't know how we're doing on time. Okay, so I have a couple of extra slides showing this in more detail. So we can actually trace what's happening with the network as it's learning. And sort of like, you see sort of like the preservation of the same dynamical systems features with some rotation of the axis. So this is what different rewards do at the end of training. If you're going back to different like earlier stages of kindergarten training, you find the same kind of encoding of reward, but in a rotated space. So you see less of it. But basically what we think is happening is that once you have the dynamical systems features, you might have to tweak them a little bit, might re-rotate them or something like that in order to make them work with the new task, but you can still recycle them for later function. Similarly, if you're looking at the representation of blocks in the inference module, this is how the average trajectories for different blocks at the end of training. And this is what it looks at the end of like pre-training with inference. So this is like another dynamical system motif where you pretty much like just copied it, like you didn't have to do much to it to keep the computation going. And I also have a cute video that shows sort of like how the flow fields evolve over training. So see, it's the same kind of dynamical system features. It gets morphed a little bit. And you might like make additional secondary structure. But there's sort of like, there's this notion that the dynamical systems features that you build originally are just like carried along for the ride for the final task. Okay, so that's it. I don't want to do the video again. I just want to go to summary. Okay, so take-home messages from this part. Like maybe this is sort of like something outside of the community, but something that's been really educational for us to sort of like think about the mechanics of what does the agent do under the hood in order to drive the behavior through the lens of dynamical systems tools. And like from this lens, what the computational building blocks that are being like combined and used in order to solve complex tasks is this creation and reshaping of slow dynamical systems features. Like from a neuroscience perspective, what was interesting to us is like that you really need to think about what information does the animal bring with it to the experiment. Like the brain is not a tabula rasa. It's not learning just this one task. That's an approach that we use a lot in neuroscience. Like if you want to like generate hypotheses about how the brain does something, you take an RNN, train it from scratch in the task that you're interested in, and hope that the solution of that will tell you things. This is like a counterexample saying that, okay, maybe like the conclusions that you're going to draw will not be very right unless you're sort of like thinking in a more nuanced way about how we got there. Yes. So this is like the final thing is that from both the perspective of the neuroscience, but also from the perspective of sort of like artificial agents, the history of experience in training can have a really important impact of the computational strategies that the final agent ends up with, which might sort of like look okay from the perspective of the task you're training on right now with respect to losses and things like that. So the reward rates for the two examples that I showed were the same, but they might behave very differently for like in generalization or for subsequent tasks. That's something worth keeping in mind. Okay, so with that, I'm going to thank you all for your attention. As I said, the primary driver of this project has been a postdoc in the lab, David Hawker, who's great. Cristina and her group have been providing the data and a lot of like neuroscientific insight into this conversation. Danilo did the statistical hierarchical latent variable model to analyze the neural activity. And Owen is a former PhD student in the lab who's been doing a lot of the groundwork for our entire pipeline for thinking about what are the dynamic systems features that networks learn and how those evolve over learning or experience. That's it.
Have lots of time for questions.
I really like the talk. I have two short questions. One would be if for an artificial task, if I have to solve, what can be a strategy I can use to select or construct these decomposition tasks?
Mhm.
And the second one would be in the entire presentation, you mostly focused on a single agent. Can this setting be also generalized to a multi-agent setting?
I haven't really thought much about the multi-agent setting one. Because sort of like, I mean, like then you get mixture of experts kind of compositionality, and I think that's potentially a little bit different in mechanism. For the how can I apply this to my task? This was a strong point of debate with our reviewers, because again, like we have like one worked out example in detail and we understand the mechanics of it. That doesn't necessarily tell you how to like apply it to absolutely anything else. I think the key ingredients is like if you can write down an approximate MDP or something of what you're trying to achieve that isolates the key computational ingredients, that helps. If you have good intuitions about what kind of sub goals or sub processes your reinforcement learning agent needs, that would definitely also help. But yes, and sort of like again, like from the sort of like generalization kindergarten experiment, we show that it doesn't have to be sort of like perfectly matched in terms of the input statistics or stuff like that. You do need to sort of like pre-train on a similar computation and the input domains to be overlapping. So that's kind of like the most general take-home messages that we got about how would I engineer this for a different task. But like I think it would be really fun to like actually think of more the reinforcement learning scenarios where this might be applicable and actually do the exercise of like taking it big scale and figuring out how far you can push it. If anybody wants to do that, let me know. It help.
Have you noticed any differences between the types of curricula that seem to work for artificial things versus what we do for humans? And if so, what would be the source of the difference?
So we have rats, we don't have humans, but sort of like it seems that there are very many curricula that behave very unrat-like. So there's, I mean, it's maybe in the nature of the task that it's sort of like the optimization landscape has a bunch of like shallow suboptima where you kind of get stuck in. And there are all sorts of ways of like cheating in like, as I said, very lazy ways to get reasonable rewards and not be bothered to do what you're actually like under the hood expected with respect to actually building a model of the world, doing inference about the states, etc. So I think we've seen like most of curricula are like hugely different as opposed to like that you actually have to work pretty hard to find a curriculum that not only does the computational well, but sort of like has the same kind of nuances that we're seeing in the animal behavior. What does that mean? I don't know. But yeah.
I have a question about the dumb rats.
Yeah.
Do they behave essentially randomly, or the systematic errors? Is there some kind of, do dumb rats look like artificial agents, or are they sort of entirely different?
That's something we haven't completely resolved. Some dumb rats are sort of like dumb for trivial reasons. But sort of like different people in Christine's lab have different degrees of tolerance to waiting. So like we have rats that have been trained to different degrees because like so some guys say like, okay, if you haven't learned anything in 3 months, I'm dropping you from the study. And like Shannon, who is here, she was like very perseverant. So like she trained them for 6 months. And some of them like stop being dumb by virtue of being trained longer. We are trying to figure out if the path to mastery looks different between the subpopulations. So we have a few ways of pooling the animals in different clusters. So one is based on the behavior. So you're fitting this online Bayesian ideal observer model to the behavior. You get the parameters from that. And you can kind of pool two subpopulations, ones that are smarter and then less smart. So that's one way. Then from the subset of animals for which you also have neural recording, we're not recording from 300 animals. That's it. It's like it's 10K pop for one of the probes. Like we're not rich enough to do that, even if we had the time. But the subset of animals where we're recording from, you can do a similar kind of separation based on the time constants of the neural activity. So you fit this hierarchical latent state space model to the neural activity. You're looking at how much stuff is going on in the slow latents. Do you actually see signatures of slow computation based on the population activity and split those up? And those have like different signatures at the level of the behavior. So there's something there. We're not quite understanding how that would be related with the different suboptimal computational strategies that we're seeing in the artificial agents yet. Maybe there's something there.
Thank you for that great talk. So, from what I understood of the way the kindergarten tasks were used to train your network, they were sort of used as auxiliary tasks that would drive features inside the network that would then be implicitly used by the policy by just learning how to leverage them. I was wondering if you have considered any mechanism to more explicitly leverage the learned solutions to these, for example, to explicitly use the predicted reward or the predicted or the counter task as input to your policy.
Oh,
or just generally.
We're sort of like partially doing that. So in one of them, we have something at 20 architecture, so we've probably done everything at some point. So we are using the header of the inference as direct input to the policy, but not for the other things. We've tried dropping that constraint, so having like completely separate heads for the kindergarten, and it still works. So it's not clear that that's changing the way the learning process works in a substantial way. But it's sort of like, it's hard to tell, like each of these networks are idiosyncratically a little bit different. Doing statistics about what's common and what's different across many networks is not that easy. So like maybe there's something there that we missed. I mean, like there's nothing stopping you. Whether it's strictly necessary is less clear to me. Yes, but sort of like the pre-training and not just auxiliary objective is important for sure.
Thank you.
Is the RL environment available?
We have this. It's not a Docker. It's something called Ocean something capsule, which is sort of like what nature journals force you to put your environments in. So that is available. Exactly how fun it is to use, you tell me. We could just do a Docker version on the web as well.
I noticed in the slide, it seems like the rats wait 9 seconds and then do the optimal thing. Is there like some model that predicts that you would wait 9 seconds and?
Yeah, so that's a very good catch. It's kind of subtle point, but the wait time as you're measuring it experimentally involves some non-decision time, because the animal, like, you're going to tell it that the reward is here. It's going to just linger around that port and wait for the reward to come. And when it decides that, oh, actually, I'm bored, I don't want to do this anymore, it needs to like walk to the other side and poke, and the sensor needs to get activated. So there's a few seconds of this sort of like non-decision cost that's kind of like morphed into how we're measuring the behavior. They are slightly suboptimal, and we're thinking that maybe there's a motivational component. Like even if you like take that out of the equation, they're still waiting a little bit longer than the optimal thing. They're hungry and they really want it, kind of business. I sort of like, I didn't show it here, but there's an entire separate decision-making process that has to do with trial initiation. The animal is self-paced, so it starts a new trial by poking in the middle whenever it feels like it. So you could have a nap or sort of like do something else for a bit. And that process is model-free, but with learning rates modulated by the beliefs of the model-based agent, which is the most bizarre thing in the universe that I continue to not understand why they would want to do that. But there's an entire additional like cognitive dimension that we're not capturing by just focusing on the trial dynamics that might also have a role.
Could you go back a few slides?
Where am I going?
The PC one where you had the curve that seemed to rotate around.
Oh yeah, the policy. Yeah.
Yeah. So when you have a rotational thing, you have previous slide.
Oh no, I wanted to go.
Yeah.
Here, yeah.
Yeah. So it's like, okay, so 2 of the dimensions are changing linearly, and one of the dimensions seems to increase and then decrease.
Well, it's a little bit tricky, right? Because sort of like we're looking in the PC space that explains maximal variability at the end of training. So like it's not clear exactly how much of information you're missing by just like looking at the wrong kind of projection. So exactly how much curvature there is in the original trajectories.
But is there any way to interpret something like why anything would increase during training and then it's all at the end, or is this like during training it's moving over time?
So the way we're doing this is sort of like, you have the super long training process. You do checkpoints once in a while. We definitely do one at the end of a stage of training. So at the end of each kindergarten task, at the end of each of the behavioral shaping steps. And sometimes we do checkpoints in the middle, but sort of like it's like there's only so much stuff you can do before you get very frustrated with compute. So it is a little bit sparse. In the older work by Owen, we we did once a really dumb brute force experiment where you have a single task, but with really complex dynamical system structure at the end of training. Is the 3-bit flip-flop tasks, for anybody who knows what that is. So where sort of like there's all the work showing that that's a universal solution. So no matter what kind of architecture, no matter how kind of like, there's a footnote, almost any training procedure that gets you to a good strategy, to good performance from the perspective of the loss will lead to exactly the same dynamical system cube structure in terms of how it solves the task. So we were trying to figure out, how do you get there? Does the training procedure get you there through different routes? Can you tell different learning rules apart by looking at this process? And what we saw there, where we sort of like, again, like the class of people hated us, but we did like time point, like epoch by epoch checkpoints. So like we actually looked super fine discretization for the entire like what happens with the dynamics. And it seems like sort of like most of the time you have some structure and you're just tweaking it geometrically. So you're like moving it in one direction or the other. And then there's phase transitions where you develop additional structure that are kind of like sparse, and they typically correspond to aha moments from the perspective of the loss. So when you see the loss like blah, 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 and then all of a sudden it drops, that tends to be correlated with the, oh, I figured out a different dynamical system motif that I can use in order to do better. But yeah, we couldn't really take that full pipeline here because the dynamical system is a lot more complicated. It's also sort of like not exactly two-dimensional. So these two flow fields are an approximation that sort of captures what's going on. Yeah, so it's like, even from a dynamical system perspective, they're kind of annoying objects to analyze, but we did our best.
Yeah, let me ask a question. Can this training be done sort of incrementally online?
So yeah, we did this batched. We have some other work where we've been playing with sort of like meta-RL objectives and sort of like online stuff. I think in principle, there's nothing that's stopping it being that way. It's just that you're going to have extra variance in the gradients. So you're going to need to do something like the very small learning rates or something to keep things from not breaking. We have a couple of follow-up projects that are potentially relevant. So we like, if you sort of like know the dynamics of learning and in deep linear feed-forward networks kind of work, or you've generalized that to recurrent neural nets, or still linear and a multitask setup where you sort of like, you define the similarity between the two tasks as in terms of the autocorrelation functions of the inputs and the outputs map that you're trying to learn. So we're trying to sort of like get more analytical tractability with respect to like the bounds of what's possible and what kind of tasks go together and what kind of tasks don't. But yeah, for the complicated scenarios, it's not like, it's not yet clear that those insights will necessarily translate in the details. It's still work in progress. Yeah, but the online setup, I mean, in principle, because like whenever you're adding a new task, the other things are still auxiliary objectives. You could do whatever you want. Like there's no like hardcore core need for batching or something like that. So probably,
Yeah,
we haven't
I
tried.
think the question because this continuous learning, people are always interested in the incremental learning, and
Yeah.
with incremental learning, you get all this problem of forgettings and all.
Yeah. So sort of like what's happening here, because you're recycling dynamical system structure, incremental could actually be better, because sort of like if you do very abrupt changes in the task, although the same dynamical system structure might be reusable for the new task, because you get like abrupt, super huge errors, and you're doing like dramatic changes in the parameters, you can like add task transitions, break the original structure that was useful, and you have to rebuild it. So we've seen in some simpler, in some simple example scenarios like that. So from that perspective, incremental is better, and sort of like online learning that sort of like allows you to figure out that, oh, what I have is actually good, might give you to like smoother transitions.
Any question? No one? Okay, let's thank the speaker again.